Hi everyone, I am Dr. Surjit Singh. Today we'll talk about the Leetcode problem of finding median of two sorted arrays. Let us begin. We are given two sorted arrays. We are to find median of the combined array. In the first method, we will use a technique similar to merge sort. A and B are the given sorted lists. We define two position variables, pos1 and pos2 as 0 and declare them as non-local in function nextMin. Function nextMin will return the minimum number out of the two lists starting from pos1 and pos2. We ensure that pos1 and pos2 are within the range of lists. We save the smaller out of the numbers at pos1 and pos2 in answer and shift its pointer to the next position and then return answer. Next call to the function will return 1 after pos1 shifts to 2. In one more such call, answer is 2 and pos2 becomes 1. Four more such calls will return 2, 3, 4 and 4. Now that one of the lists is out of range, we fetch answer from the other and move its pointer. Let us now discuss the main function and make actual calls to the function when both pointers are at 0 positions. Count equal to 9 is the total number of elements in the two lists combined, which is an odd number. So we skip the first four minimum numbers which form the first half of the combined list. Next minimum number now is 3, which is saved in answer and is returned as the median. Now consider an example in which count is an even number. We skip one less than half of the count, which in this example is 4, and then find average of two next minimum numbers, and 3.5 becomes the required median. If m and n are the sizes of the two lists, time complexity is of the order of m plus n, and the space complexity is constant. Previous method exceeds the prescribed time limit as it follows the linear search. We will now discuss the recursive binary search method. We are given two lists whose lengths are 4 and 5 and their combined count is 9. Count is an odd number, so our target position is half of count, for which we develop the recursive function getVal. The target position is 4. In the beginning, we will consider the entire ranges of both the lists. Gradually, in each call to the function, we will take decisions to bisect one of these segments of the lists. Edge case is when one of the segments is exhausted. If st1 is greater than end1, list A has been finished and target must be present in list B. st1 is the number of elements of A that are less than median, so the remaining elements of B are to be skipped to get to the target position. Similarly, if segment 2 is exhausted, median is to be extracted from appropriate position of list A. For the recursive case, we find midpoints of two segments and the values present there. If mid1 plus mid2 is less than target position, we can discard the elements of one of the lists up to its mid, for which val is lower because we know that its elements up to the mid are less than median. Remember that the two lists are sorted. In our example, val1 is less than val2, so we discard elements of A up to mid1, and in the next recursive call, we set mid1 plus 1 as the new st1. This way, we have curtailed half of the list A. New mid positions are both 2 with values 2 and 4. This time mid1 plus mid2 is not less than target position, so we will modify one of the end positions for which val is higher. In our case, val2 is higher, so we set mid2 minus 1 as n2 in the next call. We find new mid positions and their values. Mid1 plus mid2 is less than target position and val1 is not less than val2, so we shift st2 to mid2 plus 1 in the next recursive call and we find values at new mid positions. Mid1 plus mid2 is less than target position and val1 is less than val2, so we shift st1 to mid1 plus 1 and find new mid positions and their values. Mid1 plus mid2 is not less than target position and we move the end1 pointer because val1 is greater than val2. In the next call, st1 is greater than end1, which is an edge case. st1 is 3, so we discard first three elements of A and one of B. Value at target position minus st1 is 3. We return it to the previous call, which is carried by all previous calls, and it becomes the final answer for the median. In another example, count is an even number. We fix 4 and 5 as the target positions and run the program twice and find mean of the two answers. Log n is the time complexity to reduce a list of size n to be bisected to 1. But we have two lists to be bisected. In the worst case, time complexity is log m plus log n, which is of the order of log of mn. Space complexity is dependent upon the height of the call stack, which is same as the number of bisections. Therefore, it is also of the order of log of mn. We don't have to use combined count to employ binary search. This time we will limit it to one list only that reduces the time to less than half, and to reduce it further we swap the lists with each other if first one is longer. We will do binary search on A only. M and N are the lengths of the lists A and B. We define left and right as the boundaries of list A. We initiate a loop while left is less than equal to right. Mid A is the middle point of the left and right boundaries. It divides A into left and right parts. Mid B partitions list B. We may visualize the four parts as shown here. The division of B is such that the number of elements in the right part is equal to or one less than the left part. Max left A is number at mid A minus 1. However, if mid A is 0, this number is minus infinity. Similarly, we find max left B. Min right A is the number at mid A, which becomes infinity if mid A is outside of A. And finally, min right B. We notice that max left A is less than or equal to min right B, and max left B is less than or equal to min right A. Therefore, all the elements of left are less than or equal to those of the right list. Total count is 9, which is an odd number, and count of left part is one more than that of right, so the median is present in the left part. Largest of the elements of the left list is the median. So median is larger of max left A and max left B, and we return 4 as the median. In the next example, count is 10, which is even, and both left and right counts are 5 each, and the median is the average of max of the two left parts and minimum of the two right parts, which is 4.5. We are not lucky always. In this example, left and right splits as shown. Max left A is greater than min right B and the decision is not immediate. So we need to remove number 4 from the left branch, for which we move right fence to mid A minus 1, which reduces the size between left and right boundaries by half. New mid A becomes 0 and mid B becomes 5. Left and right lists now become these. However, 8 and 2 are still not at their proper sides. In order to move 2 to the left side, we move the left fence right to mid A plus 1. New mid A becomes 1 and correspondingly mid B becomes 4 and the new left and right lists become these. Now that all the left elements are less than or equal to right elements, we return median as 3. Time complexity is log of min of m and n. Space complexity is constant. I hope you enjoyed the video. Thank you for your time. Please stay tuned for more such interesting videos.